Welcome to Calculus. Today we will investigate finding average rates of change of a function on a given interval, as well as instantaneous rates of change at a single x value, focusing on the connections between the secant slope and the slope of a tangent line at a given point on the curve. We'll look at two examples and calculate both average and instantaneous rates for both. To begin, let's define average rate of change. So just again, to give a generalized curve, we'll consider that we're on the coordinate plane with a generic curve, maybe some even powered polynomial. And we'll think again first in terms of the secant line. So remember, a secant line intersects the curve in two distinct points. We'll label that as the secant line. And just recall the way we had defined the x and the y values for those points of intersection. So the right-hand x value we will call x. The left-hand x value we'll define as c. And again, if I just think about what those would be defined as in terms of y values, the upper right-hand point is f at x, and this left-hand one would have the value of f at c. So when I go to write the slope of the secant line, that would be f at x minus f at c, so the difference in the two y values of those 2 points of intersection over the difference in the x values, which would be x minus c. And we want to make a connection here. This is how we define the average rate of change of a function. And it's really over a certain x interval, a slice of the domain, average rate of change. And what we'll say is that it's on the interval from c to x. That contrasts with the idea of instantaneous rate of change. So recall what we had said, if I want to take this secant line and translate x, let it limit over towards c, and f of x at the same time is going to approach f at c, we would end up with a line that intersects in just one point, and that's our tangent line. And you can recall how we had written that algebraically. If I want to find the slope of the tangent line, I would use this same fraction setup, f at x minus f at c over x minus c. But that idea of taking the x value closer and closer and closer towards the c, we would represent by the limit as x approaches c of that same fraction, f at x minus f at c over x minus c. And what we would identify that with in terms of rate of change, that's not an average rate of change. That all of a sudden becomes an instantaneous rate of change. And it's not on an interval, it's really at c. It's the instantaneous rate of change. And what was an interval, a slice of the x values between x and c, would become simply that 1 point c. So we want to take a look at two examples where we put these two ideas of average rate of change, instantaneous rate of change into action. So let's see our first example here. Here's our function number one. It's y equals x squared plus x plus 1. Our task here is to do both of these calculations. We want to find the average rate of change of this function over the given interval. So you see our interval is here between 0 and 1. So I'm going to label those. Those are my c and my x values. Once we do that, we want to then find the instantaneous rate of change at the leftmost value of the given interval. So that's when we would calculate the limit as x approaches c, in this case 0. And then we want to graph the function by creating a table of coordinate points. So what I'd like to start with here is I want to begin actually by graphing the function. So let's create a table of coordinate points. We'll do this a little reverse, but I think seeing the function will help us interpret our two rates of change. So we'll give our x values -2 through +2, always a good starting place for our domain. And then the f of x values, which again is this function x squared plus x plus 1. So I'm going to just substitute my values in there. So that's going to be -2 squared plus -2 plus 1. So simplifying that, -2 squared is +4, -2 is 2, plus 1 is 3. Let's calculate it. -1, -1 squared plus -1 plus 1. So -1 squared is +1, -1 is 0, plus 1 is 1. At 0, we've got 0 squared plus 0. So all that's 0, plus 1 would equal 1 as well. So I can see there's some vertex probably at -0.5. See how these outputs are the same? So there's likely a vertex in between them. I believe that 1 should have the same output as -2. Let's see. So that's 1 squared plus 1 plus 1. So 1 squared is 1 plus 1 plus 1 is 3. So you can see that symmetry in the function. It's a quadratic that opens upward. At 2, we have the value 2 squared plus 2 plus 1. And that's 2 squared 4 plus 2 is 6 plus 1 is 7. So I'm going to graph this. We are graphing it first. I do think I should probably include the x value -0.5, find the coordinate of the vertex. Let's calculate that real quickly. So 0.5 squared, that's going to be 1/4. 1/2 times 1/2 is 1/4, plus 0.5. So 1/4 plus 1/2 is 3/4, plus the 1, that's going to be 1.75. Let me rethink that for a moment. That's negative. It should be lower. So it's in fact +1/4. That's the -1/2 squared minus 1/2, which would be -1/4 plus 1. So this is in fact 0.75. Okay, so now let's graph. -2 is at 3. -1 is at 1. -1/2 is at 0.75. Zeros at 1, and here you can start to use the patterning. 1's at 3 there, and then 2 we had calculated is at 7. So I could also say -3's at 7 as well. The quadratics are so symmetric. So we'll graph this function and then use the graph to help us interpret average rate of change and instantaneous rate of change. So what we're saying with average rate of change in the interval 0 to 1 is what's the rate of change between these two x values on the function. So let's calculate that value first. I'm going to give a little more room to the right here. And let's set up for average rate of change. Let's remember that formula first that we had defined average rate of change by. So remember, it's the slope of the secant line. So this is the one that does not involve the limit. So this is simply in the numerator, f of x minus f of c. over x minus c. So we'd already defined for ourselves these values x and c over here on the interval. It's x is 1, c is 0. So we can make those substitutions first. I'll write them in green because that's how I've got them labeled over here on the left. So x is 1, so 1 minus c is 0. And then from my table, I've already calculated f at x and f at c. So again, x is 1. So f at x is that output 3. Also, f at c I had calculated in the table. C itself is 0. The output there is 1. So 3 minus 1. And at that point, I just need to simplify and reduce. So 3 minus 1 is 2. 1 minus 0 is 1. So it turns out average rate of change here is simply positive 2. And we can see if I was to take and connect the two values on the function where it crosses the two boundaries of the interval. So at x is 0, x is 1, and connected those with a straight line, that would have a slope of 2. So the average rate of change, again, it's just saying overall, what's the general change from one side to the next. Let's contrast that with instantaneous rate of change. And again, we're saying as x approaches c. So as we head over towards this value of 0, as x approaches c. So remember, average rate of change is just the fraction. When I go to calculate instantaneous rate of change, that's going to be with the limit. Instantaneous rate of change. And just to make the connection again, whereas average rate of change corresponded to the slope secant, instantaneous rate of change corresponded to the tangent slope. And that does involve the limit. So we'll record that here. That is the limit as x approaches c. So x approaches 0. So notice I'm not thinking of x here as that specific value of 1. I'm letting x move kind of towards that point on the left. So in my numerator, the way that I'm going to record f of x is as the function x squared plus x plus 1 minus, now here I do want to take the value at f of c. So that had the value of 1. And that's over x minus, and our specific value for c was 0. We're letting x head over to 0. So I want to simplify that now and then take the limit, get a value. So this is the limit as x approaches 0. I can see in my original there, I can let the parentheses go, and then I've got a cancellation immediately. 1 minus 1 cancels. So on the next step, I have simply x squared plus x over x. And you can see in that form, if I were to do direct substitution, or even in the form previous to that, I'd end up with 0 squared plus 0, which is 0 over 0. And that's the indeterminate form. But I see a cancellation. Each of my terms in the numerator includes an x, and there's an x in the denominator. So I'm going to cancel this with 1x out of each term above. And what that does is eliminate that result of the indeterminate 0 over 0. So now all I've got is x plus 1, no denominator. And I'm ready for direct substitution. So instead of x there, I'm going to drop the limit symbol and call that 0 plus 1. So the instantaneous rate of change at x equals 0 is 1. And we can think that's, again, that's the slope of the tangent line. If I were to draw a tangent line that goes through 0, 1 with a slope of 1, it gives me a geometric check on what I've calculated with the algebra. So that's with a quadratic function. Our second example is with the rational parent function. So let's zoom to that example, and we'll give ourselves the 100% view. Our task is the same. We want to start off by finding the average rate of change of the function over the given interval. And then we want to calculate instantaneous rate of change at the left value of the given interval. And then we want to graph the function by creating a table of coordinate points. Let's start again by graphing. So we'll create the table, but we have some knowledge of the parent function already. We know that it has a horizontal asymptote at the x-axis, so I'm going to sketch that in. It also has a vertical asymptote at the y-axis. And then based on our memory of the function, it should have two branches, one over in quadrant 3, one in quadrant 1. But let's get some actual values with our coordinate points here. So the function is 1 over x. So simple calculation, I'm going to plug in the x value in the denominator. So that's negative 0.5. If I plug in 1, let me not jump the gun with the negative there. 1 over negative 1, that's negative 1. You can see the asymptotes representation in the table, 1 over 0, that's undefined. So a lot of times we see the table talking about asymptotes because of an undefined output. And then the branch in quadrant 1, 1 over 1 is 1, 1 over 2 is a half. So definitely this is that odd function symmetry, same values, opposite signs. So let's graph the function, and then really we're going to focus on the one in quadrant 1, but we'll graph both halves here. So at negative 2, it's at negative half. Negative 1, it's at negative 1. So the left branch is entirely in quadrant 3, and it does follow those horizontal and vertical asymptotes closely. Similarly, in quadrant 1, it's at 1, 1, 2, half, and this branch starts at the upper part of the vertical asymptote and then turns right sharply to follow the horizontal asymptote. So there's a graph of our parent function. Now, what we're interested in as we transition to average rate of change, our interval is from 1 to 4. So the c value will be 1, the x value we'll take as 4. So we're really looking, if we check out the graph from 1 to 4, so we see generally that should be, in terms of average rate of change, a negative slope. Let's calculate that. So again, I'm going to bring that one that doesn't involve the limit. So average rate of change, I'll abbreviate as ARC, is f at x minus f at c over x minus c. And we had calculated f at x and f at c in our table with c, because we got the c value is 1. So f at c is positive 1 as well. We did not calculate f at x, which was 4. So I'm going to go dot, 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 4. We're skipping over 3 there. And let's just use our table to calculate f at x. So that's going to be 1 over 4, which is 0.25. And I'll label that. So this is our x value. Again, I'm just taking that from our given interval, and then the f at x value is 0.25. So I'm ready to plug in those 4 circled values. So this becomes, in numerator, 0.25 minus 1 over 4 is my x minus 1 is my c. And let's simplify that fraction. So that becomes negative 0.75 over 3. And if I have negative 0.75 and I want to divide it into 3 equal parts, that's going to give me negative 0.25. So we can connect it over with what we see on the graph. And definitely what we're seeing is a negative slope from this left-hand value at 1 to the right-hand value of 4. And again, that would really describe what's the slope of the line segment that connects those 2 points on that right-hand branch. So the graph is a good place to check your average rate of change. It's also a good place to check the instantaneous rate of change. Let's calculate that for this function. So this is the one that, again, corresponds with the slope of the tangent line. So it involves the limiting process. We'll take the limit as x approaches the c value, which is, in this case, 1, of the function, so 1 over x, minus f at c, which we, again, have in the table here. I'll circle it as 1. So it's 1 over x minus 1 over x minus c, again, is 1. So then what I want to do is simplify that fraction. Notice that it is a complex fraction, which means I need to, my strategy here is to reduce it down so that it's not a complex fraction, but a single fraction if I can. I see that direct substitution will give me indeterminate form. If I put a 1 down here in denominator, 1 over 1 is 1, minus 1 is 0. And then in the full denominator, 1 minus 1 is 0. So it would give indeterminate form. So we got to do some simplifying before we can calculate the limit. So my strategy here is to work in the numerator and get these denominators the same. So I can think the denominator of 1 is over 1. So what I'll do is I'll multiply times x over x. Algebraically, that's like multiplying by 1. So this then becomes the limit as x approaches 1 of 1 over x minus x over x over x minus 1. So now I can combine my fractions in the numerator. We'll scroll over to the left so that the new numerator would be 1 minus x over the common denominator x over x minus 1. So again, what I'm looking for is a cancellation with that x minus 1 in the far denominator. So as I look at this numerator of the numerator, it is not the same, but it does have the same 2 terms. Switch sign. So the way I'm going to approach that is to factor out a negative 1. And then I'll start to see it's the same exact expression. So if I factor out negative 1 from 1 minus x, and then switch the terms, that's negative 1 times positive x minus 1 over x minus 1. So now, once I've got those terms identical in the denominator, I'll use the same strategy that I used in the numerator at that first step right here, that strategy. I'm going to multiply the denominator times 1 over x minus 1. And I'm also going to multiply the numerator times that same thing. What's that do for us? In the denominator, it cancels that term. Boom, boom. And then in my numerator, it also cancels that x minus 1 that I'd factored out. So what I have now is the limit as x approaches 1 of negative 1 over x. And that's very much reduced down. And at this point, I can use direct substitution because that will not give me an indeterminate form. So I'm going to drop the limit notation and write -1, substitute in the x value of 1, and that all reduces to -1. So that's my instantaneous rate of change at the x value of 1. Let's make sure I keep that in full screen mode. Let's check on our graph, make sure that lines up geometrically. So if I look here at the x value of 1, what we're saying is the slope of the tangent line at that point should be -1. So definitely, if I were to sketch that in, that looks correct. So that is the slope of the tangent line at the x value of +1. The slope there is -1 on that rational parent function. So thank you for joining for this investigation of average rate of change and instantaneous rate of change. I'm going to sign off, let you work on your problems. Thank you for joining. See you soon.